All right. So we look at a problem of prediction. So we obtain a sequence of numbers called y1, y2, and so on. And we know that they can be either 0 or 1. Okay. So yt belongs to 0 or 1, this particular set. And our goal is to predict yt. And let's say we call our prediction yt hat. Okay. And we want to do that such that the basic idea is to reduce the number of mistakes. Okay. uh, to reduce the number of mistakes. All right, so one way to write it would be we want to minimize this. Okay, whenever there is a mismatch between yt and yt hat, we are incurring a mistake. And whenever they are same, this value would be 0. So from T1 to, let's say, capital T. So if we obtain capital T observations, we want to minimize this thing. Okay. Now, the way we are modeling this thing is that these observations, these yt's, we don't know where they are coming from. They could be coming from a deterministic setup, or they could be stochastic coming from a distribution, let's say. Okay, so we say that they are coming from an unknown and unspecified mechanism. All right. And to help us with this objective, we have what we call experts. Okay. So suppose we have n experts, and each of these experts will give us his prediction, right? So we denote these by fi. So uh, every at every point, every t, we get this. Okay, all of them give us a prediction. Of course, these their prediction also belong to either 0 or 1, right? Okay. Uh, so one way to measure our, how well we are doing is uh, one objective could be to see how well we are doing as compared to the best expert in hindsight. Okay. So how, okay. Okay, so uh, let's start this. Let's start analyzing this problem, and we look to start with. We look at a special case. Okay, so let's say we know that one expert is always right. Okay, so okay, here we can observe one thing, that if this is the case when one expert never makes any mistake, then these two objectives, that is, this is number one objective and this is number two objective, let's say these are similar. Since the number of mistakes with the actual sequence would be same as number of mistakes as compared to the best expert, because best expert is telling us the exact sequence. Okay. Okay, so I'll talk about an algorithm which will help me decide this YT hat. Okay, so this is how we'll work out. Okay, so since we don't know which expert is the best expert, let's assign a weight to each expert. So we assign WJ weight equal to 1 to each expert. Okay. And how do we decide our YT hat? We simply calculate this. WJ FJ, J is equal to 1 to small n divided by n. Let us we take the average, and if this is, let's say, greater than equal to 0.5, we choose YT hat is equal to 1 and we choose 0 otherwise. Okay. Now this where this n is experts with number of experts with greater than 0. That is those with a positive rate. Okay, so I'll do an example to explain it more clearly. Okay, so what we are doing is we start by assigning a weight of 1 to each expert. Then based on that we calculate an average. Okay, and if the average is more than 0.5, we assign a weight 1, otherwise we assign a weight 0. And so after this we observe actual YT, and for all those experts which were wrong, we make their weight to 0. If whatever we calculated in the previous period by t minus 1, the actual value is, the if fj what they claim to be true was not the same as yj. Okay, so these experts can't be the one which we are looking for, which is the best expert, which never makes any mistake. Okay, so this is the algorithm we are using, and we'll see how good it performs. So I'll quickly do an example of this algorithm. So suppose we have 3 experts. Suppose the sequence that is this 1 0 1 0 1 0 1 0. So this is the yi's I'm getting, and suppose the 3 experts are there. So for t is equal to 1, let's say they gave me 1 0 and 1, and t is equal to 2, they gave me 0 1 and 1. Okay, yeah, suppose this is what I got. Now so what my algorithm will do is it will assign a weight of 1 to each of the expert, and it will calculate WJFJ by n. Okay, so initially I'll get what this would be. WJ is 1 for the first expert, the value is 1 plus 1 again, and value is 0 plus 1 again, and the value is 1 divided by 3, which is 2 by 3. So this implies my y1 hat, this is period 1. Y1 hat I choose is 1, and actual y1 is same. Okay, so from this I know that this my second expert was wrong. Okay, so I'll remove this here. So this I won't consider here at all. Okay, now I have these 2 experts left only in period 2. Okay, so let me look at period 2. Okay, the weight is 1 for each of them, so I'll get 1 times 0 plus 1 times 1 divided by 2, which is 1 by 2, which is equal to 1, which will imply from this algorithm that I choose my y2 hat to be equal to 1. Okay, which is not correct, as my actual y2 is 0. And from this I know that my first expert is also wrong. Okay, first expert is also wrong. So this is also wrong. And I know my expert 3 is the one which is always correct. And from period 3 onwards, I'll get all the correct values. Okay. All right. I'll just quickly look at what would be the how well this algorithm is. How well what can we bound the number of mistakes that this algorithm will make. Okay. Suppose the okay, we'll do it by this. Suppose sum of weights after there are m mistakes is equal to Wm. Okay. So what is, if this is the case, what is W0 when there is no mistake? So when there is no mistake, all the weights, nothing will go to 0. So that would be equal to sum of all the weights when there is no mistake is equal to n. Okay. And yeah, so m is 0 in this case and W0 is n. Okay, so now I write this thing that this Wm should be less than equal to Wm minus 1 by 2. Now, why is this the case? Okay. So this is happening because since when I made the m mistake, whatever the number of the weights in the when I made m minus 1 mistake would be, at least half of them should have made the wrong decision. That's why I got a mistake. Okay. Right. Why is that? Because half of them, since I got a wrong answer, and since it's a weighted sum, how I'm calculating the answer, I'm getting a wrong answer because half of them must have given the wrong answer. Okay. From that logic, we get Wm would be less than equal to Wm minus 1 by 2. And this recursion, when we keep on applying, we'll get this. So recursion, by recursion, I mean this can be written as Wm minus 1 by 4 and so on. We'll get Wm less than equal to W0 by 2 to the power m. And W0 is n, so this is n by 2 to the power m. Okay. And yeah. And we'll continue doing this exercise till my this I'll keep on doing till m is equal to n, right? Why is that? Oh, sorry, not this. We'll keep on doing this till my Wm is equal to 1. Because when the number of expert is remained is 1, then I know that there won't be no more mistakes because this is the one which is the perfect expert. Okay. Okay, so I'll keep on. So that this would be m star, as in the maximum number of mistakes. This is the maximum number of mistakes. Okay. So if I put it in this particular equation, I'll get 1 less than equal to n by 2 to the power m star. On solving this, we'll get m star less than equal to log n to the base 2. Okay, so this is the maximum number of mistakes I'll make given the, so it depends on number of experts, right? So if I have more number of experts, then obviously my number of mistakes would increase because I am not sure which one is the perfect expert. So if there is only one expert and I know it's a perfect expert, I'll not make any mistake at all. Okay. Yeah. Okay. So we'll look quickly at the example where this one expert never make any mistake. We remove this assumption. So we are given prediction by the expert, and we don't know whether any perfect expert is there or not. Okay. So I think, yeah. Okay. So for the general case, the algorithm is same as before. What we do is, instead of making the weight 0 when someone makes a mistake, we discount it by beta, where beta we can choose a number between 0 and 1. Okay. And we get this result. Okay. So we can bound the number of mistakes in this case also. So this is my m star. Oh, sorry. Yeah, this is not m star. So here the way I've defined is different. Here m star is the number of mistakes, least number of mistakes by any expert. So this is my best expert. Okay. In the previous case, this thing was 0. All right. And yeah. And beta was 0. Okay. So it comes out log 2. And if I put m star is equal to 0. So this is the number of mistakes made by best expert, and the number of mistakes I make is linearly dependent on. So I cannot do better than the best expert. And of course, here also log n to the base 2 is there. And as experts increase, my number of mistakes will increase. But the good thing is however, this may increase, but if I increase the number of expert, m star will decrease, as in probably it's likely that one of those experts will make less mistakes. Okay. Okay. So these are the trade-offs, or this is some basic idea about predicting a sequence of which we have no idea using experts. All right.